Alright, so we have been discussing what is a recommended system for you already, and we also define notations to be used for building recommended systems, in which can be defined as a bipartite graph. And next, we plan to discuss how to use graph neural networks for learning recommended systems and to provide a recommendation service for users inside the system, in an effective way. So the main tricky part for learning the recommended system will be lying in how to define loss functions. It will be slightly different from the loss function we define for learning the linear projection problem, in HLIN, we studied before actually. So, as we discussed before, so given the user and item pairs, we have to define a score function to measure the scores, for the pairs, right? And how likely the user will be interested in the recommendation result for the item. Also, based on the historical connection among the user and item pairs inside the recommended system, we can build a graph neural networks for learning the embedding vectors for the nodes inside them, right? In other words, given the structure of the recommended system, we can apply the graph neural networks to the graph data we have here, right? For learning the embedding vectors for all the users and items we have there. So for example, for a user U, inside a recommended system, and we can represent its embedding vector as a U vector as shown here, right? It will be a d-dimensional embedding vector for the users. For the item V inside the recommended system, we can also define its embedding vector as a V vector as shown here. It is also a d-dimensional vector embedding vector for the item as well. So given the user and item P, U and V, we can define a score function, right? It measures how likely the user will be liking this item in the recommended system based on their embeddings. In other words, we have to define a score function, combine the user vector U and V vector as shown here to define a score. So there will be different way for defining a score, connecting the for the user and item pairs. If we borrow the idea from the previous part on the linear prediction, we can define a score in another way. We can define a score as a transpose of the user representation times with one variable matrix and times with item embedding vector as shown here, right? By borrowing this function for defining score of the user item pairs we showed before, right? So besides the formula for defining scores, so there will also be some other way for defining a score as well. It depends on the application we are studying here. We can define a score in different ways. So here we don't focus on analyzing the score function in the recommended system. And here we assume we can borrow the formula we showed before for the linear prediction and borrow the function we defined before for measure the score for the user and item pairs here. Yeah, so based on the function f, we can define score for measure how likely the user U is interested in the item V as we show here, right? So, in this way, we can learn the score for the user and item pairs. Also compare the prediction of the score and versus the ground truth, we can learn the model, right? Then the tricky part for recommended system lies in how can we define the loss function. So, someone may say, can we define loss function very similar to the linear prediction we studied before? We try to maximize the scores for the positive instances and also minimize the scores for the negative instances. And here, if we assume we can extract a training set covering both the positive set E and also negative set E negative as shown here. So based on these positive and negative sets, we can use them as a training set for defining loss function for the model we started here. So for all the pairs inside the positive training set, we try to maximize the scores, right? As a summation of the log sigma function, right? So this is one way to denote this log likelihood loss function. For the positive instances, we also have this minus here. It will be similar for the negative pairs, because for the negative pair, we want to lower down, their scores instead. Therefore, we can define a term for the negative part, negative instances as log. Inside we have one minus sigma function, right, as we show here. So by combining them together, we want to minimize this loss function. In other words, we want to maximize the score for all the positive pairs and also minimize the score for the negative pairs in the training set by defining loss function in this way. This will be very similar to the linear prediction loss function we defined before, right? And we want to differentiate the positive instances from negative ones by defining loss function, for the recommended system with this log likelihood loss function as we show here. So it seems to be okay if we define this way. However, in the recommended system, it is not different. The main reason is because the data we have in the recommended system are biased. What do we mean by biased? Because in recommended system, we find the data distribution is very biased. We may have some users who are very active actually. In other words, this user will have either purchased lots of products. Those users have every rating, lots of products as well. And if we define the loss function in this way, in other words, we treat all the user item pairs equally. However, for some of the active users, we have lots of pairs which are associated for this active user, right? And if we define loss function in this way, then we want to ensure this active user will be very happy actually, because a majority of the instance property will be biased to these active users. And some of these inactive users, we ignore them because we will have so few instances associated with these inactive users. So therefore, by optimizing the loss function in this way, in other words, we are biased to improve the service for the active users to ensure they are happy with the recommendation results. At the same time, we ignore these inactive users actually, because the majority of them, they have very few instances associated with them. This is very common, right? Because if you check the Amazon, we may have some larger buyers in Amazon. They purchase lots of products. These buyers can be either some companies or some commercial institutions, right? They buy lots of products. Compared with these larger buyers, we as a regular customer, our buying records will be very limited. We only buy a few numbers of products each year, right? Then if we build the model in this way, then our service quality will be violated a lot. So to handle this kind of problem, we have to consider to define loss function in another way instead. So for building recommended system, a more common way for defining loss function is to use this Bayesian personalized ranking loss function instead. So this loss function tries to measure the quality of the recommended services for each user instead. In other words, this is a loss function that measures the personalized happiness instead. And how can we define this loss function? So from the name, we find this loss function is for each person actually. In other words, we have defined loss function from a personalized perspective. So for each user that U star we have from the recommended system, we can define a rooted positive and negative edges. The sets. What do we mean by the rooted positive and negative pairs? These edges. So in other words, all the pairs, all the edges, they will be associated to the U star actually. So for example, given the recommended system, we can extract some existing positive pairs connecting to the U star, this user, right? So we define this one as a positive set EU star. They cover all the knowing user item pairs in the recommended system. For all the pairs inside the set, they will be associated with the U star with some other items we have in the system. At the same time, we can also extract a set of rooted negative edges or pairs as well. We define the negative pairs as E negative for the U star. This one will also be associated with the U star, this user as well. And we can also extract some other potential or non-existing edges inside the recommended system. We can define this one as a negative set for the U star. They are also associated with the U star. So we find that for all the user item pairs in the positive set and negative set, they are all associated to the U star, this user actually. That's the reason why we define this one as rooted positive and negative edges, as we show here, right? So based on these two sets, we can define loss functions. And how can we define that? So let's take a look at for the user U star perspective first. So for the user U star, we have both the positive set as well as the negative set, right? Then we want to ensure this U star will receive very high quality recommendation services. In other words, for the U star, we need to ensure we are able to distinguish the positive edges from the negative ones, right? So therefore, we can define one loss term for the U star, this user specifically. So we define the loss function for U star, as shown by the formula in this part. We have loss U star, it is defined as average score. Inside we have a summation for all the user, positive pairs and negative pairs in the training state. Then inside we have one term only. This term will try to do what? This score try to distinguish the positive pairs from the negative pairs. This one denoted score we define for the positive user item pairs, right? We try to minus this one from the negative pairs. Because this one is a loss function, we want to minimize the loss function, right? And we also have minus here. In other words, we try to maximize the difference between them, right? If we define this one as a loss function in this way. In other words, we try to maximize the difference between them. This one denoting the positive user item pairs. This one denoting negative user item pairs, right? For this term, we try to encourage this term to be positive for each user. In this way, in other words, we try to ensure this positive edge score will be higher than the negative edge scores in the recommended system. I hope you can follow me, right? So this is one denoting the score for the positive pairs. This is one denoting the score for the negative pairs. If we define this term as a loss function, in other words, we try to minimize the overall term we define here, right? We are minimizing this one. However, here we have one minus here. In other words, minimization of this loss function we define here is equivalent to the maximization of this term, right? Of all the terms we define here. The maximization of the difference between the positive pairs and the negative pairs, we try to ensure the positive pairs will be higher than the negative pairs, right, as much as possible, right? So in this way, we can define loss function for the this user specifically. Then we can do what? Because here we are defining the loss function for one single user, right? Like a user as shown here, right? So inside the recommended system that we have multiple users, then we can sum all the users, their loss function together to define the overall loss function as seen at the bottom part. We calculate the average for all the users in the recommended systems and we sum their loss function, this like loss U star as shown here, together. And we define this one as the final loss function to be minimized. You can see the tricky part in this loss function is that we define loss term for a user specifically inside it, right? So no matter how biased this kind of data set is, so by defining a loss term for each user itself, and then we try to balance between, among all the users in the recommended system, right? Then we will be able to rebalance among all the users inside the recommended system to ensure all the users will receive equal quality of the recommended services, no matter how much data we have for them, right? Okay, so that's it for this part. Here we also do a quick summary for this section. In this section, we discuss two main problems for applying the graph neural networks, for learning the representation for both the heterogeneous information networks, also for the recommended systems, right? In the very beginning, we discussed what is HRIN. We provided you with the representation for HRIN as well as some examples for HRIN. Then we also discussed how to extend the GCM model, to the HRIN to learn the embedding vectors for all the nodes inside them, right? We will mention how to handle these multi-type relations inside the HRIN, and further study the link prediction problem as a task based on the embedding vectors we learn with this RGCM model, right? And then we discussed how to use the graph neural networks for learning the recommended systems. We mentioned what is the recommended system and how to use the GL models for the recommended system learning. So the recommended system will be different from the link prediction task we studied before, and we have to handle the loss function very carefully to ensure different users will receive equal quality of recommendation services inside the systems, right? Okay, so that's it for this part, and we also have some after-class tasks for this part. So please read the network embedding survey paper provided in the schedule spreadsheet. Also for the project, it's time for you to work on stage 5 of the project. I think we have covered the necessary information for the GCM model already in the previous lecture. And right now you can do the stage 5 already, based on the lecture we discussed in the previous lecture. I'd like to recommend you to start early because this one will take some time and you will also be very busy in the end of the quarter. So please consider to start as early as possible. Then you don't need to rush at the very end. Also for the exam and of the final exam, it's time for you to start going over the materials we have introduced in this class. Also summarize what we have learned so far from this course. And then we also have one lecture on the final exam in the next week, or for you as well. We will do an overview for you for the final exams. Okay, so that's it for this section, and thank you so much for your attention and time. Bye bye.